Hi everyone, Charles here for ML Papers. A very interesting research paper has caught my attention recently. This one's on transformers, which is one of the building blocks behind most modern large language models like ChatGPT. Needless to say that this is a hot topic in modern machine learning research. Little disclaimer before we start, this video belongs to the series of research paper explanations in 10 minutes give or take. It is state-of-the-art research and hence on the more technical end of the channel. So if you are new to the field, it is challenging to understand, yet if you can grasp even part of what I'm saying today, you will definitely reach a professional or close to professional level in machine learning. Today's paper is titled Transformers Provably Solve Parity Efficiently with Chain of Thought. It has been written by Juno Kim and Taiji Suzuki, and it will appear this year 2025 at a prestigious deep learning conference, iClear. In today's video, I will first present a problem called parity, which is difficult to solve for an AI algorithm. Then we will see the building block of today's paper, a transformer, which can generate a chain of thoughts. And finally, we'll see how and why it solved the problem of parity. Now, before we start, if you want to support the work that I do for free for you on this channel, that would be so great if you could give this video a thumbs up, subscribe and hit the bell icon to get notified of the next video. That's completely free for you and it really helps the channel. Thank you so much. Let's jump in. The parity problem. Take two integers k and d, like 2 and 3, and let p be a subset of k indices between 1 and d, for example 2, 3. Take a vector x of d bits, each equal to plus or minus 1. The output y is the product of all the bits contained in p. In our example, y is equal to the product of the bits 2 and 3, that is, minus 1. In the parity problem, k and d are known, but p is unknown. In our example, it can be 1, 2, 1, 3, or 2, 3. The objective of the problem is to find p based on n observations, x1, y1 to xn, yn. For example, say that you observe those x1 and y1. Then p cannot be equal to 1, 2, because the product of the first two bits in x1 is 1, while y1 is minus 1. However, p could be equal to 2, 3, since the product of the last two bits is equal to minus 1, equal to y1. But p could be equal to 1, 3 as well. This problem is extremely challenging, because the least little mistake in p can make the prediction y completely wrong. This technicality is exacerbated when k is equal to half of d, where each index has half a chance to be in p, giving you an exponentially large number of potential candidates for p. As a matter of fact, even basic neural networks cannot solve this problem, but we'll come back on this later. Transformers and chain of thoughts. For now, we are going to introduce the building block of our solution with a chain of thoughts transformer. Heuristically, when tackling a difficult problem, the chain of thoughts transformer does exactly what a human being would do. It generates a sequence of intermediate steps and advances step by step, little by little, until the final solution. Just like you and I would solve this very hard calculation in block by first introducing an intermediate step before finally reaching the final result. The chain of thoughts transformer is parameterized by matrix W, which will be made explicit later. Our objective is, given n-bit vectors x1 to xn, to be able to generate a vector of all the outputs y1 to yn. For that purpose, we first read the bit vectors x1 to xn column-wise. The first column b1 is a vector composed of the first bit of all the observations. The second column b2 contains the second bit of the observations, and so on until the dth column bd. The chain of thoughts transformer will generate a sequence of k-1 vectors bd plus 1, bd plus 2 to bd plus k-1, which will reflect better and better on the solution. Finally, the chain of thoughts transformer will output the last vector bd plus k-1 as an estimate of y. The generation process is as follows. At every step m between 1 and k-1, the transformer computes the vector bd plus m as phi of zd plus m, where phi is a function which looks like this. The vector zd plus m is defined as a convex combination of b1 to bd plus m minus 1. And the convex coefficients are softmax function of the upper part of the nth column w circled in red on the screen. And the softmax function is defined on the screen. Now, if that can help, here is an explicit formula for the coefficients. Now, visually, it is interesting to see that each new vector bd plus m depends on all the previous bi's from 1 to d plus m minus 1, not only via the convex combination, but also via each of the coefficients within the sum. And therefore, the chain of thoughts transformer estimates y by the final output bd plus k minus 1, whose many interconnections with all the previous bi's can capture the complex structure of the parity problem. With teacher forcing. Now, it's time to see what we do with the matrix W and how we train this model. Precisely, we first initialize the matrix W at the value W0 is equal to 0. Then we compute the output of a chain of thoughts transformer with matrix W0, which gives the output vector bd plus k minus 1, 0. This yields an error or loss, L of W0, compared to the true output vector y. We can then compute a better value of y by gradient descent update, W1 equal to W0 minus eta gradient of L of W, where eta is a learning rate. We can then compute the output of a chain of thoughts transformer with matrix W1, which yields the output vector bd plus k minus 1, 1. This yields a loss L of W1 compared to the true output vector y. We can then compute a better value W by gradient descent update, W2 is equal to W1 minus eta gradient of L of W, and so on for as many steps as you want. And that's roughly it. Roughly, because this does not work. Let me tell you why. Within the chain of thoughts transformer, if you make the least little error in the computation of bd plus 1, then this error will cause an error in bd plus 2. Then bd plus 1 and bd plus 2 are both erratic, yielding an increased error in bd plus 3, and so on until bd plus k minus 1, where the error has basically gone out of control. So we need to control the error or loss at every single step of the computation. As a first toy setting, the authors considered the case where one has access to the ground truth intermediate states. In other words, to train our model, we may utilize not only x1, y1 to xn, yn, but also all of the intermediate steps big ground truth d plus 1, big ground truth d plus 2, to big ground truth d plus k minus 1. The first step is to incorporate all the loss terms into the loss function. Rather than just the final output term, we consider the sum of the losses at all the steps from 1 to k minus 1. Next, remember that for any m from 1 to k minus 1, bd plus m suffers from the error of all the previous bit vectors. So the term bd plus m minus b ground truth d plus m squared does not isolate the loss from step m. To thwart that problem, we leverage the fact that we know the ground truth intermediate vectors big ground truth i's, and we replace the bi's by them in a chain of thoughts transformer model formula. With a bit of imagination, it is like a teacher forcing the ground truth at every single step of a process, and this is called teacher forcing. The authors prove that teacher forcing works, provided, of course, that we have access to the ground truth intermediate steps. Now, what happens outside of this toy setting? Without teacher forcing. Remember, the main issue is the propagation of the error across a chain of thought steps, because an error at one step impacts all of the following steps. So we're essentially going to perform two tricks to avoid that issue. Trick number 1, autoregressivity. Let's get back to our parity problem and consider the more complex case when k is equal to d out of 2. d is equal to 8 and thus k is equal to 4. Consider one observation of d is equal to 8 bits, b1 to b8. And assume that y is equal to the product b2, b3, b5, b7. The product y can be decomposed into the product of b2, b3 and b5, b7. Now in our chain of thoughts, we can envision the following 11 steps. For the first 8 steps, there is no choice, those have to be the observed single bits b1 to b8. Next, we may want the following two steps to the two subproducts b9, which is equal to b2, b3, and b10, which is equal to b5, b7. And for the final step, it is the outcome y equal to b11, which is also equal to the product b9, b10. This gives us a big binary tree, but if we look carefully, b10 does not really depend on b9, but only on the b1 to b8. In fact, every element in our tree only depends on the elements which are at a lower level, and not on the elements at the same level. And therefore, in the initial formula expressing B10 as a convex combination of B1 to B9, we can rewrite this formula differently to express it as a convex combination of B1 to B8. And more generally, we can express each new step by convex combination of all the steps at a lower level in a tree. As a result, no information navigates horizontally on the tree, that is to the nodes of the same level. In particular, errors no longer propagate horizontally on the tree, and this trick is called autoregressivity. Trick number 2, data augmentation for filtering. Now, to keep this video reasonably short, I won't get into too many details for this one, but a global idea is to add synthetic data to the model and to safety check the model consistency on those supplemental data and filter out the seemingly inconsistent intermediate bit vectors among the BD plus 1 to BD plus K minus 1. Now, the main result of the paper is that the method works. Good news. And more precisely, for any positive epsilon, if n is larger than d to the 2 plus epsilon, then a chain of thoughts transformer without teacher forcing with log k gradient updates achieves an error lower than exponential of minus d to the epsilon out of 16 with large probability. In contrast, building on previous works, the authors further showed that a standard method which does not utilize a chain of thoughts type mechanism and paired with a standard gradient descent update would require at least d to the 15 plus epsilon observations to achieve a small error. The reason behind this, and probably the main message for today, is that if you want to learn a very difficult problem like parity, your model needs to incorporate the interactions between the observations and cross-reference between them rather than just look at them individually. If you want to know more about this interesting paper, I will put the link in the description box down below. In particular, there are synthetic data experiments and more details on the results. As always, if you enjoyed this video, please give it a thumbs up, subscribe and hit the bell icon. I would really appreciate your support. Thanks again so much for watching. I wish you a wonderful week and I'll see you in the next video. Cheers.